Hi, so this is lecture 22 of MA 221, and today I'll be discussing about Taylor's and Maclaurin polynomials. So you might remember in Calc 1, there was a term naming linear approximation. So if you look closely, what is derivative? Derivative at, say, this point, say this is the graph of a function, fx. Okay. And let me just use some different color. So this is the function fx, y is equal to fx. So at the point AFA, if I draw the tangent line, then we know that the equation of this line looks like y minus fa is equal to f prime a x minus a. This is the tangent line passing through this point AFA, right? And then I can rewrite this as y is equal to f a plus f prime a x minus a. So in like simple terms, derivative actually gives a linear approximation to the graph of the function. Okay, so this is basically tangent line. Now, so the first degree Taylor polynomial of fx about x equal to a is the degree 1 polynomial px, where px is equal to a naught plus a1 x minus a, but it has to satisfy two conditions. One is p of a should match with f of a, and p prime a should be matching with f prime a. Okay. Similarly, the second order approximation to fx at x equal to a would be px is equal to a naught plus a1 x minus a plus a2 x minus a square, right? Degree 2, so that's therefore a minus 2 square. But then this px, so basically px is a 2-degree polynomial, but it has to satisfy following condition. pa is same as fa, p prime a is same as f prime a, and then p double prime a is same as f double prime a. Okay. And so like by the same language, we can say that the nth degree Taylor polynomial for fx at x equal to a. So this x equal to a basically symbolizes that it is the polynomial is centered at a. Okay, so then t and x will look like so t and x will be something like a naught plus a1 x minus a plus a2 x minus a square, just like the degree 1 and 2 polynomials, an x minus a to the n, with the following properties. Tn a should be fa, tn prime a should be f prime a, and so on. Tn, the nth derivative at a should be fn derivative at a. Okay. That means function and the first n derivatives agrees at x equal to a. Okay. Let me demonstrate an example. Say my fx, the function fx is sine x. Then for that, the 0-degree Taylor polynomial will be like constant 0. The 1st-degree polynomial will be x. The 2nd-degree polynomial will be again x. 3rd degree will be x minus x to the 3rd over 6. 5th degree will be x minus x to the 3rd over 6 plus x to the 5 over 120. Okay, and so on. I can uh, go on and like evaluate T7, T8, T9, and so on. So what actually happening with this T1, T2, T3, T5, and so on? So if you look carefully, we are trying to approximate the graph of the function by using some polynomials. Why polynomials? Because polynomials are like very easy to draw, and then properties of polynomial functions are like quite nice. So if I look at this example, so say this green line is a graph of sine x. Okay, this is my y equal to sine x, and then t1 is this red line. So you can see that the red line is approximating, but like from here to here. Within this short range, t1 is a good approximation. But if you say, so this is so in this short range, this red line is giving a good approximation. But if you consider, like further away from that region, then t1 is like far away from the graph of sine x. Okay, cool. But then t2 is like same as t1, but t3, which is x minus 6 to the third over 6, and the graph of that is this blue line. Now see, the blue line is better than t1 approximation. And then again t5, which is like which is like this purple line, this is even better than t1 and as well as t3. So if you consider more and more powers of x, for example t7, t9, and so on, then those polynomials will be like better approximating the function itself. Okay, cool. Now, so I know that t2 is something like this. It should have 2 degree in terms of it should have degree 2 in terms of x, and also it should satisfy these 3 conditions. But what is exactly t2x? Let us find that. Okay, so I know that t2x is a naught plus a1x minus a plus a2x minus a squared, right? But then I also know that t2 prime should be if I do the derivative straight away, I'll get this, right? And if I take the second derivative, then I'll get 2a2. Okay. Now the conditions that we have is t2 at the point A should be fa, and if I consider this, then I'll get fa is same as a naught. Similarly, for the second condition is t2 prime a is same as f prime a. If I put x equal to a back in there, then I'll get what? I'll get a1 to be f prime a, right? Similarly, t2 double prime a. So if I put this x equal to a in here, I'll get 2a2. Okay, the condition is never mind, f double prime a. So then I'll get 2a2 to be same as f double prime a. In other words, a2 is f double prime a over 2, right? So therefore, t2x. So what I'm doing is I'm trying to find the coefficients that was unknown to me. Okay, I found all 3 coefficients here in the polynomial approximation. So therefore, my t2x will be what? F of a plus f prime a x minus a plus f double prime a over 2 x minus a squared, right? Okay. Now, in general, if I go on and like try to find what will be the exact formula for n degree Taylor polynomial, so that is denoted by tnx, and tnx should be of this form: if a plus f prime a x minus a plus f double prime a over 2 factorial x minus a square plus so on, if nth derivative at a over n factorial x minus a to the n. So this is basically the nth degree Taylor polynomial. Okay. And in short sum, I can write this as like this. X minus a to the j, where f0 at a is just fa and 0 factorial is 1. Okay, cool. Now, when my a is 0, so remember I defined what is what do you mean by center of a Taylor polynomial. So when the center is 0, that means you have only x to the power something in the Taylor polynomial, then that is all that is named Maclaurin polynomials. Okay, so the Maclaurin polynomial of the degree n will look like f0. Remember, the a is replaced, all the a's will be replaced by 0 for Maclaurin polynomial. So I'll get f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus so on f n derivative at 0 over n factorial x to the n. Okay, cool. Now let us see some examples to better understand this. Okay, so for this example, we need to find the T3x, that means 3-degree Taylor polynomial for the function fx given as square root x, and the center is x equal to 4. So that means our a is 4. Okay, so remember my T3x has this form. F at 4 plus f prime at 4 x minus 4 plus f double prime at 4 over 2 factorial x minus 4 square. The degree should be 3, so f triple prime at 4 over 3 factorial x minus 4 whole to the third. So basically, I use this formula. I took a to be this a to be 4, and I consider x minus a to the third, this term. I went till this term. Okay, I neglected all the higher degree because I know that my n is 3 in the given problem. Okay, cool. So therefore I need to find the first derivative, second derivative, and third derivative. And let me just try to evaluate those. So x to the half is the function. F prime x is just half x to the minus half. F double prime x is minus 1/4 x to the minus 3 over 2. F triple prime x is just 3 over 8 x to the minus 5 over 2. Now f at 4 will be square root 4, which is 2. F prime at 4 will be 1 by 2 square root 4, which is 1 over 4. F double prime at 4 is minus 1 over 4, and then this. So if you try to evaluate this using calculator, you'll get this, and f triple prime 4 will be just 3 over 8 square root 4 to the 5. Let me just clear this a little bit. So this will be 3 over 256. Okay, now just put all the values in. So 2 plus 1 over 4 x minus 4 minus 1 over 32, and there is one more 2 because there's just 2 factorial there. Okay, x minus 4 square, and then plus 3 over 256 over 3 factorial x minus 4 to the third. Let me just slide one more line to just simplify it a little bit. So 1/64 x minus 4 square plus 1/512 x minus 4 to the third. Okay. So if you evaluate till this, it is fine. You don't have to like again square and like cube the polynomials. It will be like very nasty. So it's fine if you just calculate till this point. Okay. So the next example is you have to find the Maclaurin polynomial for fx, which is equal to e to the x. So here your a is just 0. Everything else, the general formula for Taylor polynomial will follow. So for this problem, yeah, so my fx is e to the x, right? Okay, so fx is e to the x. So f prime x will be again e to the x, and so on till f n of x is same e to the x. So f of 0 will be e to the 0, which is 1. F prime of 0 will be again 1, and so on. F nth derivative at 0 will be again 1. All of this are e to the 0, so 1. Okay, so t n x, if I use the formula, it will be f0 plus f prime 0 times x plus f double prime 0 over 2 factorial x square plus so on f n derivative at 0 x to the n over n factorial. If I put all the values, then I'll get 1 plus x squared over 2 factorial plus so on x to the n over n factorial. And that's it. This is the nth degree Taylor polynomial, or like Maclaurin polynomial for e to the x. Okay. Next problem, again, you have to find Maclaurin polynomial for fx to be cosine x. Okay. But here there is no mention of the degree. So basically, say nth degree. Okay. So again, t and x will be f of 0 plus f prime 0 times x plus f double prime 0 x square over 2 factorial plus so on f n derivative at 0 over n factorial x to the n. Okay. So my fx this time is cosine x. Okay. F prime x will be minus sine x. F double prime x will be minus cosine x, and f triple prime or x is again sine x. F fourth derivative of fx of cosine x will be again cosine x, and so on. Okay, so I have to basically catch the pattern. So f0 is 1, f prime 0 is 0, f double prime 0 is minus cosine 0, which is minus 1. F triple prime 0 will be sine 0, which is 0. And then again, f fourth derivative at 0 will be 1. Okay. And then again, the same sort of, so at fourth derivative, I'll get back cosine, right? So again, for fifth derivative, I'll get minus sine x, which is first derivative. So again, I'll get the repetition. Okay, so my pattern will look like this. Let me just shift this here. So the coefficients will be 1, 0, minus 1, 0, 1. And then again, repetition of this. So this one is there, and then again 0, minus 1, 0, 1, and so on. Okay. So my polynomial will look like 1. This will be vanished. This term actually, the whole term will be vanished because f prime 0 is 0. Okay. So I'll get directly this term. So x squared over 2 is there, and the coefficient is -1, so minus. Then again, plus x to the 4 over 4 factorial, because so here I have f third derivative 0, x to the 3 over 3 factorial, right? But the coefficient f triple derivative at 0 is 0, right? So it'll vanish. I'll get the next term, which is x to the 4 over 4 factorial, and the coefficient is again 1, right? And it will basically repeat. So x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and so on. The last term will be -1 to the k, x to the 2k over 2k factorial. Okay. Because I see that x squared is there, the next term is x to the 4. So, only the even power will be surviving. So x squared there, x4 there, x to the 6 there, x to the 8 there. So last term will be x to the 2k, something like this. When n is equal to 2k, right? Or n equal to 2k plus 1. So it doesn't matter n is even or odd, the last term will be this. This will be the last term. Okay. Okay, I hope this example is clear. This is a little bit subtle, but if you have any problem, you again go back and try to get that. So I have written some of the important Maclaurin series for some basic functions. So e to the x has this series as Maclaurin polynomial. This is for cosine x, this is for sine, this is for cosine hyperbolic, this is for sine hyperbolic, this is for 1 over 1 minus x, and then the last one is for ln 1 plus x. So a good thing or good exercise would be to see some of this, to evaluate some of this Maclaurin polynomial. You do the derivative and try to get this result. Okay. Now, one important thing is, so what basically we are doing using Taylor or Maclaurin polynomial, we're trying to approximate, right? If you go back to the graph of sine, which I have drawn, basically, yeah, this one. So basically, I'm trying to approximate the, various kind of functions with polynomials, right? So wherever there is a question of approximation, there should be always another question, how good the approximation is. So always there should be a question about error. Okay, so the next portion is about getting what is the error in that approximation. Okay, so as n increases, my t and x will be better approximation function for fx. But the question is how good an approximation t and x is for fx. So there's a theorem which is also known as Taylor's theorem, which says that our Rnx, where Rnx is like error in nth degree Taylor polynomial, and that is given by fn plus 1 derivative at c x minus a to the n plus 1 over n plus 1 factorial. Okay, this is the formula. And for Maclaurin series, your a will be like Maclaurin polynomial rather, your a will be 0. Okay, so let me solve some of the examples on this regard. So this example is asking you to use the Maclaurin polynomial t3x for fx to be ln 1 plus x to approximate ln 1 plus 1. Okay, so say you don't know what is how the logarithm actually behaves. You just can use the Taylor approximation. Okay, so I'll skip the very first details that you need to fill, but believe me that ln 1 plus x will be, say, g3x, and this will be x minus half x squared plus 1 over 6, I guess, sorry, 1 over 3, x to the 3. So how I get this? Again, the same thing. Do the derivative, first derivative, second derivative, and third derivative, evaluate at 0, and then try to figure out which term will be vanishing and which term will be surviving. Okay, so, and after that, you just basically put x to be 0.1, right? So 0.1 minus half 0.1 square plus 1/3 0.1 to the third. On the left hand side, you have ln 1.1. On the right hand side, if I use calculator, I'll get 0.9, 0.09533, and so on. Okay. So see, you don't even need calculator to get the value of ln 1.1. So that is a very good example or application of Taylor's polynomial. Okay. Now, the one question might be how good this approximation is. So remember, ln 1.1 is not exactly same as this. This is a very, very good approximation, but is not an exact value. So how far we are from exact value? So we know that ln 1 plus x minus t3x, which is basically r, this is nothing but r3x, right? This is by the formula that I mentioned here. This is f fourth derivative at c. There's modulus, right? Oh, okay. I missed the modulus somehow. Yeah, so this is the actual formula. So, you know, it'll be, yeah, so it'll be f fourth derivative at c, and then x to the 4 modulus there over 4 factorial, right? So n is 3 there. So I get f to the f fourth derivative and 4 factorial in the bottom. Okay, now I have to estimate what is let me just get some more space. So I have to estimate what is f fourth derivative at c. Remember, c is oh, I didn't mention c. What is c for? So c is some value between x and a. Okay, but what is a here? Remember, a here was 0 and x I choose to be 0.1. Okay, so f fourth derivative at c would be, so I try to bound this. This is so let me just write f fourth derivative at x minus 6 over 1 plus x to the 4. You can get that, not a big deal. But then this is nothing but 6 over 1 plus c to the 4, right? Where c is in between 0 and 0.1, right? Between a and x. A is 0, x is 0.1. So far, so good. But then this is less than 6, right? Because c is in between 0 and 0.1. So I can write this. Okay, but then from this line, what follows is our R3 x modulus is less or equal to 6 over 4 factorial times 0.1 to the 4, right? Because x is 0.1, so Yeah. And this is nothing but 0.000025. Okay. So this is the error with the exact value of ln 1.1. So this value minus this value, if I take the modulus, will be something like this. So you see that this error is so small. So this is a very good approximation. Okay, so you see one of the examples of the error approximation. Let me solve one more problem having fourth root of x. Okay, so in this problem, I have to approximate fourth root of 1.1, and I have to use third degree binomial expansion. So what is 1.1? So 1.1 is 1 plus 1/10, right? So fourth root of 1.1 is just 1 plus 1/10 over 1/4. Okay. So again, remember there is one formula. Okay. So before that, I need to introduce what is binomial expansion. Okay, just give me a minute to like get some page, and then I'll just shift it. So a quick note about binomial expansion. So the question is, what is the Maclaurin polynomial of degree n for fx to be 1 plus x to the k? Okay. So again, your fx in this case is 1 plus x to the k. Your f prime x will be k 1 plus x to the k minus 1. And the other derivative will follow. F0 will be 1, f prime 0 will be k, and all the other derivative will follow. F double prime will be k times k minus 1, and so on. Okay. So if I try to evaluate t and x, the Maclaurin polynomial for the function 1 plus x to the k, I'll get f of 0 plus the formula. You should already try to memorize it. Basically, it just goes. This should be 1 plus kx plus k times k minus 1 over 2 x square plus k times k minus 1. A little bit more space. K times k minus 1, k minus 2, x to the third over 3 factorial plus so on. So basically, this is called the binomial expansion for 1 plus x to the k. Okay, so you can see this is of the form 1 plus x to the k, where k is 1/4. Okay, so you can directly use the formula, and if we do that, then we'll get something like 1 plus 1/4 1/10 plus 1/4 times 1/4 minus 1 1/10 square over 2 factorial plus 1/4 time 1/4 minus 1 minus 2 1 minus 10 to the third over 3 factorial. Remember, in the problem, I need to go till third degree binomial expansion. So basically, I should stop there, just there, x to the third. And here my x is 1/10. So 1/10 to the third will be my last term. I should stop right there. And then if I use calculator, I'll get this to be 1.02411171 and so on. Okay. So fourth root of 1.1 is 1.02411171. I should write this curly equal to sign because this is an approximation. Now, as usual, your next question should be how good the approximation is. I mean, what is the error? Your error should be by that formula less than modulus 1/4 times 1/4 minus 1, 1/4 minus 2, 1/4 minus 3. How I got this term? Over 4 factorial. And there is times 1 times 1/10 to the 4. Okay. So remember, this is a third degree approximation. So if I go back to the formula, so this here, my n is 3 in the formula if I put that. So I should be evaluating f for the derivative at the point C and then x to the 4 over 4 factorial. That is what I have done there. There is some more calculation involved in this. I guess you can figure out that. So basically, like the previous problem where I have tried to estimate what is the fourth derivative, you need to do the same thing for the next problem as well. But that is not like too difficult to figure out. So I'll leave that to you. And this will be 3.76 times 10 to the minus 6. So this is a pretty good approximation. Okay, so that is it. And for the next problem where you have to again estimate sine 1/3 with the Maclaurin polynomial, there what you have to do is like kind of do the same thing again. Okay, so fx is sine x given, f prime x is cosine x, f double prime x is minus sine x, f third derivative at x is minus cosine x, and then repetition, right? Again, if I get the fourth derivative, I'll get sine x back again, which is this. And then again, take derivative to get cosine. So these are basically the 4 terms, and then these 4 terms will get repeated again and again. Okay. So f of 0 is 0, f prime of 0 is 1, f double prime of 0 is 0, f triple prime of 0 is minus 1, and then repetition. Okay. And f n plus 1 derivative at c would be plus or minus sine c or plus or minus cosine c, right? Because we are getting, sine and cosine with probably some change of sign every time we take the derivative. So in other words, if n plus 1 derivative at c, if I take the modulus, will be less or equal to 1. Okay. So yeah, sine 1/3, if I approximate as third degree polynomial, then I'll get 1/3 minus 1/3 to the, okay. But before that, what is the general formula? Okay, so Tnx, if I try to get that, it'll be, or rather T3x. T3x will be x minus x to the third over 3 factorial from all of this calculation that I have done. Okay, just put the values in the general nth degree Taylor polynomial and you will get the answer. Okay, cool. So sine 1/3 will be 1/3 minus 1/3 to the third over 3 factorial, right? And using calculator again, this value will be this, and that is nothing but 0.32716 and so on. Okay. But if I use the calculator, the actual value will be 0.32719. Okay, so you see that in the 1, 2, 3, 4, fifth term after the decimal, like the the point, I'm getting the error. Okay. So the error R3 for the third degree approximation is less than, so F fourth derivative at C modulus over 4 factorial and then x to the 4. But this thing is less than or equal to 1, right? By this logic. And then I have x to the 4 modulus over 4 factorial. But when my x is like 1/3, right? Yeah, so x is 1/3. I choose that value to evaluate. So this will be like 1/3 to the 4 over 4 factorial. And this thing is 0.000514. So see again, the error should start from the fourth term after the point. And that is basically happening there. Okay. Okay. So, this is it for today's lecture. So I have completed Taylor and Maclaurin polynomial. There should be one more lecture on Taylor series. So Taylor series and Taylor polynomial are two different things. Hopefully I will be able to like upload that lecture tomorrow along with the practice exam. So be a little bit patient to that. Yeah, thank you.